For part 3, let's talk about something called continuous collision detection. Now, the reason for this is what we call the bullet through paper problem, or often you hear that called tunneling. Now, what are we talking about? If you have something that moves fast, like say a bullet, and it is heading towards something that's really thin, like a piece of paper. Now, remembering that in a game, things don't move continuously. They move discretely. We'll move things a frame at a time, which means really, if you look closely, you'll see that things jump forward. And now with a fast moving bullet and a thin sheet of paper, it's very easy for a bullet to pass through the paper in a single frame. Like on one frame, it was on the front side of the paper. On the next frame, it's on the back side of the paper. It never hit the paper. And so just using a collision detection routine would not notice that the bullet was supposed to hit the paper. I have a card here, a picture of a bullet going through a car. That's not really what we're talking about, but it's a cool picture. We're talking about where the bullet would be going like face on at the paper so that it would be thin in that direction. Like this diagram here. So the bullet was here, and then the bullet was here, and then there's a piece of paper in between, and the bullet never touched, right? In reality, it's a better idea for something like a bullet to model it not as a sphere, but to model it as a line segment, where the beginning point of line segment is where the bullet was on the previous frame, and the end point of the line segment is where that bullet is now, and that'll avoid the bullet going through the paper problem. But sometimes there's larger things that you don't want to model as this infinitesimally skinny, thin little bullet, like a line segment. Maybe it's a stone or a baseball. You throw a baseball at a wall, and the baseball is big enough that you don't want to consider it just as a point, and you don't want to approximate its motion as a single line segment. So what we'll do is what we call continuous collision detection, or CCD for short. And there's a number of approaches to that. I mean, like, for example, a baseball, you could model that as a sphere. And if you say the sphere started at this point here, and the sphere ends at this point, we could sweep the sphere. We do a swept sphere, which is to imagine the sphere at its beginning point, the sphere at its end point, and all the places in between if it moved in a linear fashion from one to the other. We'll say we'll sweep it, like it'll sweep through time. Like we start the sphere here, and then we move it linearly in this direction, and all the spaces it occupies in between there, that's the shape that we make. And that final shape is a capsule, like a Tylenol capsule or something. And the beauty of this is we can solve this analytically. We can do sphere versus capsule or capsule versus capsule with math. We can work the math for that just using a little algebra. It's a quadratic equation, and that we can solve. And that's pretty cool. That's one of the reasons that we like spheres so much. But some things just are not spherical, right? And so we'll need some way to do some arbitrary shape. So what I'm going to introduce here, what I'm going to talk about is taking a convex polygon. We talked about the fact that if you had two convex polygons, like the blue one and the red one, that you could find a separating axis between them. So what if we could sweep the convex polygon? And that's what we're going to do here. We say that the polygon started here, it ends at this location, and if we have a convex polygon sweeping to another location, the shape that it sweeps through is also a convex polygon, right? So if you just think of it, all you do is you connect the outside edges of the original position and the new position, and you'll get an overall convex polygon. And so if you have some way to ask, do two convex polygons overlap, then you could test the blue sphere, the blue shape versus the red shape. But you could also test this swept shape versus the red shape. And And next time we'll talk about the GJK algorithm, which will let us do something like that. But for now, let's just assume we have a way to do that, and let's talk about how we'd use it for this continuous collision detection. Okay, so here I just have the blue shape fully swept, and we can see, I think clearly, that it is supposed to intersect with that red shape. But there are a few problems because we've made some assumptions here. First assumption we made was that the thing moved linearly. And what if it was rotating, right? So let's say, for example, in this case, we have this blue rectangle that starts here and it ends over here. If we sweep it by just creating, the outer boundaries around it, we'll get these lines that we have here, and we'll see that this swept shape clips through the red shape. However, once we recognize that how it really moved, or how it was supposed to have moved, was like this, by rotating while it was moving, we'll see that actually the blue shape wasn't supposed to touch the red shape at all. And perhaps worse, the blue shape moved outside of the bounds of that swept shape that we're using to approximate its motion. And so if the red shape was up here, it was supposed to have touched it, but it won't. So that's one of the problems that we get with the swept shape. Another problem that comes up with a swept shape situation is oftentimes someone's going to ask for more precise information than just, did you hit it? They're going to say, well, where did you hit it? Or another way of thinking this is, when did you hit it? I mean, we're thinking of this blue swept shape as swept through time. This is over the course of a game frame where the shape started here and it moved along this path until it would have arrived here. But in this case, we need to say, oh, but it can't get there because this red thing is in the way, right? So the blue shape was supposed to go this way, and then somewhere right about, I don't know, in here somewhere, it was supposed to bang into that red shape and then change its trajectory. We'll need to calculate exactly where that happens. So one approach is to iterate. We'll say that this is time equals 0, this is time equals 1. Now find me at what time t the intersection first occurred. We'll say that's where it bumps. And we can do this iteratively, which is sort of a by guess and by golly. You try it here and try it there. Let me give you an example. For example, I've determined that these two shapes did intersect somewhere between time 0 and time 1. So let's try time 0.5. And so at 0.5, we can see that the shapes do not intersect yet. So we'll go in between. So now we know it's somewhere between 0.5 and 1. So we'll go in between there. At time 0.75, they do intersect. So that narrows it down to somewhere between 0.5 and 0.75. So we'll split that in half again, and we'll see, oh, at 0.625, they intersected already. So we'll keep doing that. We'll keep iterating until we've refined the time step down as small as we're wanting to. It's a toss-up between how many iterations you want to do versus how much precision you want. And, that's just going to come down to how much time you want to spend doing this. Speaking of time, doing all these collision tests over and over and over again as we're iterating is obviously going to take a lot of time. It's going to multiply the number of collision tests we're doing by a dramatic amount. So because of this, you don't want to be doing this iterative method unless you're already pretty sure that the things collide in the first place, right? So in the next video, we'll talk about that a little bit more.